Hello there. This is the video on chapter 3. So I'm going to maybe do 3 videos on chapter 3. This is the first one. And so let's get started. I hope you're doing well. So let's see. So this video will be on these 3 sections right here from chapter 3. So we're going to talk about functions and relations and function notation, domain and range, and then rates of change and behavior of a function. So let's start by looking at the first section, and then as we progress, I'm going to explain any concepts that needs to be explained. Okay, so let's do that. Looks like let's see, my mouse is connected here. Picking up the wrong pen. Okay, there you go. So what we have, here you go, I got it finally. So let's do some of these problems in this section. So here I'm going to start with number 8 and 9. Looks like, there you go. So number 8 and 9, there you go. This is number 8 and 9. Let me see what kind of view I have here. Let me change the view so we see it better. So I'm going to work with number 8 and 9. Okay, so what we are asked to do here is, it says for the following exercises, determine whether the relation represents y as a function of x. So let's talk about that idea. So I'm going to get some area here so we can work on it. So I'm going to give you some examples of a relation. So in algebra, a relation is basically a set of ordered pairs. For example, this is a relation, right? So 1 is related to 4, 2 is related to 5, 3 is related to 6. And this is another relation. So in this relation, we have 1, 2, and 3, and then we have 4, 4, and 4, right? And then here is another relation. We have a set of ordered pairs 1, 1, 2, and then 3, 4, 5. Now, all of these are relations because there are a set of ordered pairs. Now, this one, the x values and the y values never repeat, right? And in this one, the y values repeat, and this one, the x values repeat. So these are all relations, and they're useful in many applications. But the ones that are useful for us are the ones that we can write this way. We can say we have a situation here when we have input, and then we have output. So we have input and we have output. So what we like to do is this. We like a relation that works for this. So if I come to work and I want to input 1 here, I know that the output is going to be 4, right? So if the input is 2, I know the output is going to be 5. So that's the first one, right? This is a 5 here. And if the input is 3, then the output is 6. So that works. So the first one is good. I can use it in applications when we have input and output. What about this one? Well, this one works too, because all I can do is I can set up a system here, and then if somebody says 1, I say, well, the output is 4. And if somebody comes in and says, what about the output for 2? I say, well, it's 4. And what about output for 3? Well, also is 4. So there is no confusion here. For every input, we get an output, and there is no confusion. Now, the confusion starts in this one, because if I set up the same system as input and output, right? So what is the output for 1, right? What is the output for 1? Well, it says 1 goes to 3 and then 1 goes to 4. So there are two different outputs for the same input. So when we have a relation that the input repeats, we say this is a relation, but it's not really going to function for us in this setup, right? So these two are functions. The relations we call functions, and this one is just a relation. It's not a function. Now, when we say function, as you see, we define function as a relation where input values don't repeat. So that's why this one is not a function. Now, so with our definition, it depends on what? What is the output? What is the input? So when I say this is not a function, I assume that this second number is the output and this one is the input. If we make that assumption, then we can say this is not a function, but these two are functions. That's all there is to it. All right, so now the function can be given in many different forms. For example, I can give another example before I do 8 and 9, okay? So let's say 1 goes to 3 and 2 goes to 5 and so forth. And in general, if you have an x goes to 2 times x plus 1, right? So that's a function. So we can also write it this way. We can say y equals to 2x plus 1, right? And in this case, is this a function? Yes, because the input doesn't repeat, right? For every input, we have a unique output, right, for that input. You know, tomorrow you come in and put 1 in here, you still get 3. Day after tomorrow, you still get 3. Now, instead of writing the output equals to 2 times input plus 1, that's what this is, we write something like this. And this idea is called function notation. So it's a notation we use to indicate that here this relation is a function. That's all there is to it. So when you see this, you read it as f of x. F of x. F of x equals to 2x plus 1. Now, f of x is the name of the function. Now, some people said it equal to y, is the same as y, but it represents y, it is not y. F of x is the name of the function, and then y is the output variable, right here. So if you put, x here, this would be f of x, which is the output. And then the formula goes inside here, which is the rule of the function. So that's what this function does. All right, so that's all there is to it. So now, can we represent a relation differently? So we can represent relations or functions with tables, with algebraic equations, or in the coordinate plane, we can graph this. As you know, we can go to 1, that's the y-intercept, and go up 2, and right 1, and then graph it. So every graph in a 2D coordinate plane is what? Coordinate plane is a relation. Every graph is a relation. Now, some graphs are functions, but all of them are relations. So this is in the form of a graph, we can represent this function. We can represent it algebraically, or we can represent it in a tabular form. All right, now that we have talked about this, now we can do number 8 and number 9. Now the question is, it says, is y a function of x, right? That's what we are asked to do. See, it says for the following exercises, determine whether the relation represents y as a function of x. Is it? Well, to do that, we need to solve for y. So we get 2y equals to negative 5x plus 10, right? We have to move the 5x to this side. And then divide everything by 2. So y equals to what? Negative 5 over 2x plus 10 divided by 2 is 5, which is here is written as 5 minus 5 over 2x, which is the same. Now, does this prove that y is a function of x? Yes, because you can argue that for every x value, you get a unique y value. There is no way today you put a 0 for x, you get 5, and then tomorrow come back, you put 0, you get something else. It's not possible. So that proves that this represents y as a function of x. All right, now what about number 9? Well, y equals to x squared, so yes, this is a function y, because for every x value, whatever the x value is, the y value would be whatever that is squared. And there is no way you can get the same, you get different answers if you have the same x value. All right, so these two are functions. Okay, so let's do another one. Let's do number 27. 27. So in 27 it says to do what? Let's see what we have to do. For the following exercises, evaluate the function f as the indicated value. So what do we mean by evaluating a function? What do we mean by that? Well, what we mean is this. So let me do some of it up here. So what we have here is a function. So we can write it here as an input-output kind of machine, right? So I can write it like f of x. Well, actually, let's do it. I don't know why I can erase, but it should be. Okay, so I'm going to write it this way. So here's a machine, here's the input, and the output is, the name of it is f of x. I'm just going to put f of x. And the rule of it is 2x minus 5. So what do we mean by, first of all, how do you read this? Well, we read it as f of negative 3. And what we mean by that is that if we input negative 3, what would the output be? Now the output would be, if you, well, this formula says 2 times input, right? 2 times input minus 5. So that's what I'm going to do. I'm going to do 2 times input minus 5, which is going to be what? Is going to be negative 6 minus 5, which is negative 11, right? So that's negative 11. Similarly, f of 2 means what? It means that we substitute 2 for the input and we get negative 1, right? What does that mean? That means that if 2 is the input, then the output is negative 1, right? So that right there is x, and this right here is f of x, right? All right, and what about f of negative a? Well, it doesn't matter. Whatever the input is, we say 2 times whatever the input is minus 5. Now in this case, we cannot just do the operations because we don't know what a is, but we can simplify it. So 2 times negative a is negative 2a minus 5, right? And now what is negative f of a? So here, before I forget, if the input is negative a and the output is 2a, negative 2a minus 5, like that. Now if we know a, then we know this ordered pair, right? Okay, negative f of a is negative whatever f of a is. So what is f of a? So we're going to put it in parentheses. F of a would be, if you substitute what? A for x. So it would be 2 times a minus 5, which is negative 2a plus 5, right? So that's negative f of a. And then the last one is f of a plus h. Again, we said we don't care what the input is, whatever it is, we just put it for what? For x here, because the rule says 2 times x minus 5. So minus 5, that would be a plus h. Again, we can't do the operations, but we can simplify them. So we can't just get a number out of this because we don't know what a is and we don't know what h is. But we can simplify it. So we get 2a plus 2h minus 5. Okay? So that's what this is. All right. So let me move on to number 32 and 33. Let's do 32 and 33 and give us some. So number 32, it says, if you have a function like this, evaluate this thing right here. Now, what is that? Well, it's function notation, so we understand what it is, right? Because it's function notation. This right here says, what is the output for x plus h? And this right here, it says the output for x, which is this whole thing, right? That's the output for x. And this is just h. So we have to separately, figure these out and subtract them. Well, what is g of x plus h? Well, g of x says what? G of x says take 5 and subtract the input squared, right? Now, if input is x plus h, then we're going to have to write x plus h here and then simplify it. And you know that x plus h squared is not x squared plus h squared, but is h squared plus 2hx plus h squared, right? So what we get here, I'm going to directly right there. So that is what we're going to get for g of x plus h. But also we have to subtract from it what? So we have to, so it's right here. So that is our g of x plus h. And then this right here is our g of x, right? It says g of x plus h minus g of x. So that's g of x plus h minus g of x. And then divide by h. That's divide by h. Okay, now simplifying this requires that identity. A plus b squared is a squared minus 2ab plus b squared. So here a is 5, here a is x, and b is h, right? And if you do that, you get here, that's what you get, and then you have to distribute this minus, right? And then also you distribute this minus, and you end up with this And to simplify this, let me do it right here. So we get 5 minus x squared minus 2xh minus h squared minus 5 plus x squared, because that would be minus 5 plus x squared. Now this x squared cancels this x squared, and the denominator is h, right? And this 5 cancels that 5. So what you're left with is this, and is right here, over h. Now we can simplify further. We can factor the h out and then cancel it, right? And there's a negative there still, so it would be negative 2x minus h. And h, remember, cannot be 0 because we are dividing by h. Okay, so that's number 32, and it's about what? That is structure that is very famous in mathematics. In calculus, you start with something like that. That's the rate of change between 2 points, actually. That's what that is. So if you have a function, right, let's say this is in general, this is not this g of x, it's just in general. Let's call it f of x. And if this is x, and this right here, x plus h, then this would be f of x, and this number is f of x plus h. So what we just did here, this expression that is a famous expression in mathematics, is nothing but the slope of this line that goes through what? These 2 points. And that line is called the secant line. So this expression that we just talked about is called the slope of the secant line. Sometimes they write it as m, and there is a secant here. That means the slope of the secant line between x and x plus h. Now what's the slope? The slope would be f of x plus h. That's y2 minus y1 minus y1 divided by x2 minus x1. It would be x plus h minus x. And you see these two cancel, we get that expression that we were working with. So this expression, which is f of x plus h minus f of x over h, is a famous expression, is called difference quotient. Difference quotient. No. Is it called difference quotient? What do you think? Is it called difference quotient? Yes. Difference quotient. Now, but you could call it slope of a secant line. All right, so now let's go to the next one. This was number 32. So we're going to do number 33. Let's do number 33. Where's number 33? It's right here. So this one is the same expression, but is given in a different form. So still is difference quotient, but is given in this form. So you see, in this case, if you do the same thing, you think of a function, right? And you have 2 points. And instead of calling this x and calling the other one x plus h, we could call this a and we can call this x. And the same setup, this is f of a, and this one would be f of x. So now we can write that the slope of the secant, which is this line that goes through this point, these points, is y2 minus y1, which is f of x minus f of a divided by x minus a. See, x2 minus x1. So that's another form of the same thing, difference quotient. Sometimes it's written this way, because in calculus it's easier sometimes to use this structure instead of the other one. And you should be able to do it. So it's the same kind of idea. You see, f of x is just this whole thing. So we put it here. minus, now in this case it's not f, it's g, doesn't matter. So g of x is this thing, so we put it here. So g of x, which is that, right? Minus is part of the formula, g of a, that means take this and substitute a for x, and we did here. And then divided by what? X minus a. Now we simplify that. Again, this x squared plus is, you have to distribute the minus. So what do you get? You get x squared plus 2x minus a squared minus 2a, right? That's what we're going to get. And that's what this is. You just put, you can put these together and put these together, so we can do factoring by grouping, right? Because these two have in common something, right? Or these two, doesn't matter. You can actually do it this way. So we can factor what these two have in common. What do they have in common? X. And what do they have in common? A. And see if we can factor it. Or, so let's see. So x squared. So what do we get if we factor the x out? We get what? We get x plus 2 here. And what do we get over here? We get a minus 2, right? That's not very useful, right? So what do we do? So we can factor this out. Well, we can actually add something to it, so we can factor it. So if we keep the, if we multiply by something, so we can factor it. So let's see what we can do here to factor it. Let me erase all this. So we have to use a trick to factor this, so we can get x minus a out of it. If we can get x minus a out of here, we can simplify it, right? So we need x minus a out of here. Now we know x squared minus a squared, right, is nothing but what? Because we have a what do we call this? Did you say identity? Yes. We have an identity that is the difference of quotient, difference of the two squares, right? Difference of two squares, and this looks like this. Now here we have x squared and a squared, so that's x minus a times x plus a. And then plus, now you see these two have what in common? 2 in common, so we could get x minus a out of that. Now these two have x minus a in common, so we can factor it out, right? So writing it this way allows us to get x minus a out of it. These two have x minus a in common, you see, and we factor it out. If you take x minus a out of here, you get x plus a. If you take x minus a out of here, you get 2. So basically now we can cancel that, and then we get this expression, except we have to indicate that x cannot be a, because if x is a, the denominator is 0. Okay, so that's number 33. Now let's do number, let's do something 38. Let's do number 38. So 38, what are we supposed to do? It says given this function, let's get some area so we can work on. So it says given this function, f of x equals the square root of x plus 2. Find f of 7. Now f of 7 is easy to find. What does that mean? We don't understand what it means. It means that we're looking for an ordered pair. 7 is the input. We want to know what that output is. And that output is actually f of 7. So how do we find it? We substitute in here 7 plus 2, and we get 3, right? All right. Now, what is, now the question is, so this is A part. Now the B part, it says solve this. What does that mean? See, it says f of x equals to 4. What does that mean? Well, it means that in this case, the output is 4. We're looking for the input that gives you that output. So this right here is the x we're looking for, right? So the question here, there was that if we have x, what's f of x? Here, if we have f of x, what is x? So how do we solve this? Well, we know what f of x is, right? So we say this has to be, this is f of x, this has to equal to 4. So we solve this radical equation, which we talked about in chapter 2. You have to square both sides, so you get x plus 2 equals to 16, so x is 14, right? So that's the answer to B part. All right, let's do one more of these. Let's do number 39 as well, now that we are at it, right? So consider the relationship that, write the relationship as a function of what? F of t. Evaluate f of negative 3. So what we like to do is this. We like to have something in terms of t. That means we want to get r by itself, right? And we want r to be a function of t. That means we have to solve for r here. So 3r equals to 18 minus 2t, right? So r equals to 18 divided by 3 is 6 minus 2 divided by 3, right? Now we're going to call this r what? F of t. So f of t equals to 6 minus 2/3 t. Now what is f of negative 3? Well, that means if t, this time t is the input, if t is negative 3, what is f of negative 3? And this number would be f of negative 3, which is 6 minus 2 over 3 times negative 2 over 3 times negative 3. Now this negative 3 cancels this, right? So this is actually 6 plus what? 6 plus 2, which is 8, right? All right, so that's number 39. Let's do a few more from this section, and then we are done with it. Let's do also number 40 and 41. Number 40. It says, for the following exercises, use the vertical line test to determine which graphs show relations that are functions. Now remember we said that in order for a relation to be a function, the input cannot repeat. Now how can you catch it if somebody gives you a function, right? Let's say, for example, this function. This is a function. That means y is a function of x. How do we know that? Because for every x value, there is only one y value. Now, what about this function here? Well, this function as well. How can we know that? Well, we have to check every x, right? But instead, can we just scan this with a vertical line and see if the graph crosses the vertical line more than once, then is not a function. For example, if we have a relation that looks like this, well, obviously for all of these x values, we have two different y values, right? See? For this x value, we have two different y values. So this is not a function. So this idea is called a vertical line test. So what we do, we scan this with a vertical line. If there is more than one intersection, then it's not a function. Now obviously this one is a function, right? So number 40 is a function. Now what about number 41, which is this one here? Is that a function? No, because it doesn't pass the vertical line test, right? Okay, what about number 46? Let's do number 46. What about this one? Is this a function? Well, this one is a little, well, it's not harder, it's just a little trickier. Because if you do a vertical line here, does it cross at 2 points? No, because this point is what? This point is hollow, it's not filled. That means this x value has only one y value, and that's that one. This is not the y value. The same is true over here, right? This x value, 0, has only one y value, and that's the y value. So if somebody says, what's f of 0? You should say -3, not 3, because it is what? Is empty. So based on this idea, vertical line test tells us that what? That this is this a function? Well, yes, on those 2 points you're right. But what about these? You see, for this x value, we got two different what? Two different y values. For these ones too. For these ones too. So this is not a function based on our test, right? All right. So now let's do number 52. It says, given the following graph, now we have to evaluate all that using the graph. We are not given a formula, we are given what? A graph. Remember we said a function can be given in a table or equation or graph. So this is given in terms of a graph, right? So what is f of -1? That means if x is -1, right, what is y? Well, if we have a graph, we have to go to x -1, go up to the graph where you hit the graph right there. That y value is what? Is f of -1, right? So f of -1 is what? Is 1, right? Now, then it says solve for what? Then it says solve for this. What does that mean again? Well, we talked about that. This means that if the y is 3, what is x, right? Well, we go to 3 here in the y, and then we go to the function about right there. We see that is what? That is 7. So the answer to this is x is 7. It is 7 that has the output of what? Of 3. Okay, let's do 2 more from this section and then we are done. And that is, let's say, number 66. Now I have to change the view so I can see the numbers. So let me go to web, because the numbers are not filling in for that view. So let me go down to 66, which is right here, right? So 66, it says f of 3. I couldn't see it. So let me go back to web. So say, oh, here we go. We got it. So 66 is find f of 3, and this is what we are given. Right? So let's pick it so we can actually work with it. So let's get that much. So we are given a function in form of a table, right? And it says, what's f of 3? Well, we go to 3 here. F of 3 is what? 53. So that's 53. All right, and let's do one more, and that is number, let's see, 74. In 74, it says find 74, it says, for the following exercises, evaluate the expressions given function f, g, and h. So these are the functions that we are given, and we want to evaluate what? We want to evaluate this right there. So I'm going to do number 74. 74 is this one. Now, these are the functions, and we want to find these. So this expression says take 3 and multiply it by what? By f of, multiply it by f of 1, then subtract from it 4 times what? G of negative 2. So we're going to put 3 here, and then we want to find f of 1 minus 4, and we want to find g of negative 2. So this goes here, and this goes there. So let's find them. What's f of 1? Well, f of 1, I'm going to have to use this. Is 3 times 1 minus 2, right? 3 times 1 minus 2, and that is 1. So that's 1. And what is g of negative 2? Well, g of negative 2 is that one right there. So I have to put 5 minus negative 2 squared, right? Don't multiply that before you raise it to second power. So that would be 5 minus 4, which is, again, 1, right? So that's 1, too. So what's 3 times 1 minus 4 times 1 is negative 1, right? That's how we do that. All right. So that's the section 3.1. I think we did enough of these. Now we want to go to section 3.2. We're not, see how far we have gone. I think we can do another section before. So let's do another section. So what is section 3.2 is about domain and range, right? That's what 3.2 is. So let's do some problems from that section and understand what it means to find domain and range. So we're going to do 7 and 8 as 2 examples. All right. So now the question is, what is domain and what is range? Now, in a if you're given a table, domain and range is obvious. For example, if I give you this relation, right? Domain is basically a set of numbers, right, that you pick the input from. The set of numbers here would be just those 3 numbers. And the range is a set of numbers that you put your outputs in. So this set is basically a set of all the outputs that you can get. In this case, this function has only 3 input values and 3 output values. But of course, not all functions are like that. You can have, for example, f of x equals to 5 minus 2x squared. So input and output values for these functions are a different story, because we have infinite number of numbers. It's not only 3 numbers. So what we do in this situation, we find the domain easily, and the range we have to actually graph the function in order to find the range. So we're going to talk about the range later. For now, we concentrate on finding the domain. If you're given an equation, we concentrate on the domain. Now there are two types of domain. There is the domain that is basically mathematically what kind of numbers can I substitute for x here and get an output. Well, mathematically you can put any number you like, and we represent that by what? All real numbers, negative infinity to infinity. So any number works for this. Now what causes problem then? What is it that stops us from substituting some other numbers for x? Well, there are two problems. One problem is when we have a radical and then we have n, and n is an even number. Remember, if the index of a radical is even, inside cannot be what? Cannot be negative number. So this number right here has to be what? Has to be greater than or equal to 0. Otherwise, this doesn't make sense. For example, square root of -4 is not a real number. I know we can make sense of it as a complex number, but it's not a real number. Now, what about 4th root of -16? That doesn't make sense either, right? So any even number will not work. So what do we do when we have radicals? We have to make sure the stuff that is inside, which is called radicand, has to be greater than or equal to 0. Another limitation that we might have is when we have a denominator. If we have an expression that has a denominator, the denominator cannot be 0. So if we have one of these, then we have to make sure that when we write the domain, we have to exclude the numbers that make the denominator 0. And if we have one of these, we have to exclude all the numbers that make the expression here negative. Now, it's kind of hard to exclude all the ones that make it negative because there are lots of numbers that do that. So if we have one of these, instead of finding the numbers that don't work, we're going to find the numbers that actually do work, and we concentrate on those. If we have one of these with denominator, then we're going to just exclude the numbers that make the denominator 0. All right, so number 7, the domain is all real numbers. Now what about this one, number 8? Well, for number 8 we have one of these. So what we have to do is this. We have to set the inside of the radical greater than or equal to 0, and we have to solve this inequality. And that we did that in chapter 2. So we add 2 to both sides. So you see, in this case, we just found the numbers that do work, and that's the domain. So if you put it on number line, that means go to 2 and every number to the right of it. So that means 2, right, comma what? Comma infinity. That's how we write it. Okay, now let's do a few more in this section. Let's do number 14. So number 14, and we're going to do number 16 as well, so pick both of them. 14 and 16. So let's do both. So here we go. So number 14 is the one that has a denominator problem, right? So basically what we have to do, we have to take the denominator and set it equal to 0, and then solve that equation. We get 6. So we write that domain is basically, well, let's put it on the number line first. Let me put it on the number line. So domain is every number except for 6. So we put the 6 here, put a hole here, so it's not, so kind of can, but it's empty. But everything else is good. So everything else is good. But we don't want that number. So the domain is all real numbers except for 6. So we can write it this way. From negative infinity to 6, not including 6, right? From negative infinity all the way to 6. And then from 6 to what? To infinity. And then we put a union in between. Or we can write what? In set notation. We can write domain is all real numbers x such that, this little thing means such that x is not what? Is not 6. And that's it. So that's the domain with 14. Now what about number 16? Well, number 16 we have two problems. We have the denominator and we have that thing. So we have to deal with those separately and then combine them. So let's see. For the top, x plus 4 has to be greater than or equal to 0. That means x has to be greater than or equal to negative 4. So let's put it on a number line here. So for this to work, x has to be what? Anything greater than negative 4, including negative 4, is good, right? All right, for the denominator, not to mess things up, x minus 4 cannot be 0. So we set it equal to 0 and we say x is 4. So for the denominator, basically everything is good except for number 4, which is right there. Everything else is good. Now, of course, for this fraction to work, the numbers have to come from here, and so the numbers have to satisfy this and this, because if you, for example, pick a number 4 here, it's good for the numerator, but it's not good for the denominator, so the fraction doesn't work. So what do we have to do? We have to see what these two have in common, right? What do these two have in common? When we see what they have in common, they have in common everything except for, everything to the right of negative 4, except for what? Except for 4, right? So what can we do? Well, we can write negative 4 is good, right? So we're going to include negative 4 because it's here and here. But these numbers are no good, right? So all the numbers all the way to 4 are good, but the 4 is not good. We put a parenthesis for that. And then union, all the numbers here, they're good in both places. So that would be from 4 to what? To infinity. So that's the domain for this. We have to take all the problems into account, right? All right, so that's number 16. So let's do, let's see, let's do 22 maybe. Here's another one. Let's do 22. All right, so here what we have is, so here we have again 2 problems and 3 problems, right? Because one problem is that x minus 4 has to be greater than or equal to 0. So from here, we know x has to be greater than or equal to 4. That means here's 4. 4 is good, and everything after is good. That would make sense for the numerator. But what's the problem with the denominator itself? Well, denominator, this x minus 6, first of all, has to be greater than or equal to 0. But x minus 6 cannot be 0, right? Since we can combine these two and we say, okay, we just take care of that by what? By getting rid of that equality. Here we just put greater than. If I just put greater than here, that takes care of the problem of this denominator cannot be 0, right? So we don't have to you don't have to worry about this because we already took care of it over here. Got rid of the equal sign. So from here, this is x greater than what? 6. So that means if x is not 6, but is everything after 6, that's good for the denominator and for the radical in the denominator. So again, we have to figure out what these have in common, right? They have nothing in common here, so it's over here, right? So they have this part in common, nothing here, right? So they have this part, this part in common, right there. So the answer is going to be what? Starting from 6, not including 6, and going to infinity. So that's the domain that works for number 22. All right, so let's do one more. Let's do number 26. Find the domain of this function by using algebra and then graphing it. So let's do. So by using algebra, how do we do that? Well, we know that, go up a little bit. So we know that 2x to the third minus 50x has to be greater than or equal to 0 for this to work, right? So that means what? Well, we have to solve this inequality, which is polynomial inequality. So let's factor the 2x out of it. So we get 2x, and then that's x squared minus 25 has to be greater than or equal to 0. Now remember, to solve inequalities like this, first we convert it to an equation and we solve it. So either this equals to 0, which means x equals to 0, or x squared minus 25 equals to 0. So that means x squared is 25, so x is plus and minus 5, right? So x is plus and minus 5. Now, here's the number line. We know those numbers, right? Those numbers make, so there is 5, negative 5 here, and there is 0 here, and there is 5 here. We know those numbers make this what? 0, and it's good because we want it to be greater than or equal to 0. So we have no problems with these numbers. Those three numbers are good. Now the problem is, what about these numbers? Do they work? Well, we test them. So second step is to graph the solutions, and we did. So graph the solutions, and we did. So we graph the solutions right here. And then the third step is to take test points. Test points. Or test numbers. So we're going to pick, there are 1, 2, 3, 4 regions here. We're going to pick a number here. Pick a number here, maybe -1. Pick a number here. And pick a number here. And test them. Where? Over here. So if I put -6 here, this would be negative, and this would be positive. Positive times negative is negative. So I don't want these numbers because they make what? They make this negative. What about -1? If we put -1 here, that would be -2, right? What would that be? Well, -1 squared is +1. Minus 25, that's a negative number. So negative times the negative is positive. So that's good. I want all the numbers here are good. What about +1? Well, +1 here, that would be positive, and this thing would be negative. Negative times positive, not good. And what about, so we don't want these numbers. What about 6? 6 is positive. 6 here will give you positive. Positive times positive is positive. So these are good as well. So the domain of this function is going to be what? Is going to be those numbers, right? So I'm talking about this one, right? So don't get this is from previous problem. I'm talking about this one. All right, so from -5 to 0, union from 5 to infinity. That's the domain that we get. So from -5, including -5, to 0, including 0, union 5 to infinity. That's the domain. Now, if we graph this function with the calculator, so here's the calculator you can use in this course. So we're going to graph it. Now, we don't want to graph this to find the domain of it, right? Instead, we can graph the inside and see where this inside is positive from the graph. So let me show you. So I don't want to graph the square root of this. I'm just going to graph 2x to the third power minus 50x and zoom 6. Well, zoom 6 is, I don't see, you know, I'm going to change it to make it. So what I'm going to do, so instead of the calculator, we're going to get a more powerful tool, and that is what? That is the program Algebra, which is free. You can download it and use it on your computer. So what I'm going to do is this. I'm going to get inside here, which is what? What was it? 2x to the third. So I'm going to put 2x to the third power minus 50x there. So the calculator was a little, you know, the standard window wouldn't work because this thing is, you know, has large values. So let me use this GeoGebra. So you see, that's what it looks like. And as you see here, let me make sure I have the 5 there. So you see, inside of this radical is positive. Where? Positive means above x-axis, right? So from -5 to 0, as you see, is positive, and is after 5 is positive. Between 0 and 5 is negative, and before -5 is negative. You see that? So when the function is above when the y values are above the x-axis, then it's good. So that's what they mean, graph it and see. So in order to see it with the calculator, you have to keep zooming out in order to see it, right? You have to keep zooming out, right? You have to keep zooming out until you see it. And you have to press trace first. Here we go. Forgot to put trace. And then zoom out. So you have to keep zooming out in order to see it. Otherwise you don't see it. All right. So so that is number 26. And now we want to do number 27. For the following exercises, write the domain and range from the graph. So we can do that. If we are given a graph, we can actually find domain and range easily. So domain is all the x values, right? Now these x values over here are not part of the domain because there are no points over here, right? So we have to start maybe here, and then you see you go to 2. So the domain values are basically starting from 2, not including 2 because there is no what? There is no point here for 2. but right after 2 is good. And we go all the way to number 8, and that's it. That's the domain. Now, what is the range? Well, the range is the y values. So the y values, as you notice here, go from 6 to 8 and not including 8. So the y values go to 6 to 8, not including 8, right? So remember, these are y's and these are x's. Okay, so let's do number 30. Here you go. Says the graph, the domain. What's the domain? You can see it here, right? So domain is from 2 to what? To 8, and the range is from, we have to say smaller number first, from 2 to 6, right? From 2 to 6, negative. You don't see the negative ones here. Actually, it's negative. It's from -6 to -2. I don't know why we don't see the negative numbers here. But these are negative numbers. Somehow I didn't catch it, but so these are negative numbers, right? So x is from 2 to 6, including 2 and 6. So domain is 2 to 6. And the range is from -6 to what? To -2. Remember the interval notation, we put the smaller number first and then the bigger number. So that's the domain and range for number 30. Now what about number 32? What's the domain for this one? Well, let's see. So here the domain goes, basically x values go from -3, and then we have all points here all the way to 2, right? So from -3, including -3, to 2, but 2 is an empty space here, so 2 is not included. So that's the domain. Now what about the range? Well, the range starts from -5, and we have y values all the way to what? To 4. Now this empty space has a y point here, right? So that, don't count that for y, because y is filled in for y. You see, here f of -2 is 0, right there. So y values are basically go from y coordinates, go from -5 to 4, right? Including -5 and including 4. Okay, all right. And now what about number 35? It says the graph extends horizontally from that. So here we go, this is number 35. So here the domain goes from, you see there's a point there, so it goes from -6 all the way to what? To this number, which is -1/6, and then jumps, this is no point, there are no points here, jumps to 1/6 all the way to 6. So the domain is from -6 to -1/6, union from 1/6 to 6, right? And the range is going to be from what? So that's the domain. So range is going to be from this number all the way to whatever the y coordinate is here. So it goes from -6 to -1/6, union, and from 1/6 to 6, right? So as you see it right here, so that's the domain, and the range is what I just described, right? So that's, oops, and that's the range right there. Get it back, here we go. So that's the domain and that's the range. See, from -6 to -1/6, union from 1/6 to 6. All right, so that was, what number was it? 35. Okay, let's do one more, number 38. It says, for the following exercises, sketch a graph of piecewise function. All right, so these kind of functions are called piecewise function. Why? Because they have two pieces, right? See, there are two pieces. So what you see over here is the domain of the function broken into two parts, right? So basically what it says here is that if x is to the left of -2, this function looks like x plus 1, which is like that, right? And if x is to the right of -2, this function is -2x minus 3, which is what? You go to -3, and then you go down 2 and right 1, like that. So basically this graph looks like this to the right of -2 and looks like this to the left of -2. So how do we go about graphing this? Well, we're going to graph it one piece at a time. But the number that breaks the domain into two parts, we're going to go to that number first, -2. So we're going to go to -2, and we say, okay, we are supposed to use -2 for that function. So let's substitute -2 for x here. If I put -2 for x, what do I get? Well, I get 4 minus 3, which is 1. And that would be a point on this line. So 1 is over here, so here's a point. Now, where am I supposed to use this? To the right of -2. And I know this is a line, so I need one more point to the right of -2. Well, I'm going to use what? I'm going to use 0. So that's -3. So at 0, this is at what? At -3. Right? So I'm going to go what? I'm going to do this. I'm going to, well, connect these 2 points and then keep going that way. So that's one part of this function, the bottom part. Now, to the left of this point, I have to use this. But here's the question. How close can I get to -2 to see where this function is? Well, it looks like there is no way we can get as close as possible, because there is no limit to it. You can get as close as you want to -2. For example, -1.999999999, right? So in order to get rid of that confusion, we are going to just use -2 in here and see what happens. Well, if I put -2 here, which I'm not supposed to, because it says when x is -2, use this, right? See equality here? So when the domain value is -2, use this. So I'm going to use -2 here. I get what? I get -1. What I'm going to do, I'm going to graph -2, -1 as a whole. So I go to -2, -1, and I'm going to put a hole there. See this -1, right? See, that's the point. But I don't put a filled in because I know when x is -2, I'm supposed to use that one. Okay, so I got a point actually on this line. It's an empty point, but that's okay. I know where I am. Now, what I need another point to the left of -2. Let's say -3. So if I put -3 here, what do I get? I get -2. So here's -2, -1, -2, there. So I'm going to connect them, and then I know the rest of it would be a straight line. So that's the graph of this what? Piecewise function. It's the graph of this piecewise function, which looks like this here. All right, so that was 38. So let's do 41. So again, I want to graph this. This is a piecewise function. How do we go about doing this? Well, I know that to the left of 0, this function looks like just the line that goes through 3, like that, right? And to the right of 0, and at 0, is going to look like what? It's going to look like this. So let's do it. So again, we go to the point that breaks the domain 0. At 0, this, we're supposed to use this, square root of 0 is 0, so that's the point on this. And I know to the right of 0, it looks like the square root of x. We can get another point, but I know, we already know this looks like what? It looks like that. But we can get another point. Let's say, for example, 1, 2, 3, 4. If I put 4 here, square root of 4 is 2. So let's say we get that point. And then we graph it. All right. Now, to the left of 0, I'm supposed to use this. But again, no, illegally, we're going to use what? 0, 4 here, since there is no x here. When x is 0, y is 3, according to what? According to this part of the function. But again, this gives us what? A whole, not a filled in. So 0 and 3 is right here. So this is going to be a whole, not a complete point. And then to the left of it, whatever number you pick, you always get 3. So basically it's a horizontal line this way, right? And that's number 41. All right, now let's do number 46. Now in number 46, we are not supposed to graph it. We are supposed to find these values. And this is important to understand that a piecewise function can have one piece at a time. You cannot have a function that has all these pieces at the same time, at the same value of the domain. So this right here says when x is less than -2, the function looks like that, and you have to use that to find the function values. And when x is greater than or equal to -2, you're supposed to use that one. So for example, what's f of -3? Well, -3 is where? Is it here or here? Well, -3 is to the left of -2, so it's going to have to use that one. So to find f of -3, you just get -3 plus 1, which is -2. Now, what about -2? Well, -2 looks like equal to -2 is here, so we're going to have to use this one. So we just put -2 here. -2 times -2 minus 3 is 1. And then f of -1, where is -1? Well, -1 is to the right of -2 on the number line, right? This is -2, this is -1. So we have to use this one. Again, we put -1 in there, and we get -1. And 0, well, 0 is way over here to the right of -2. So we have to use this. And that's how we get -3. All right, so that's number 46. And let's do 2 more, and then we're going to end this video and do another video. So 53. 53, it says the function is defined for all x values. So now this one right here. So what's the domain of this function? Well, let's see, number 53. So what's the domain of this function? Well, the domain is given here. Looks like all the numbers to the left of 1, so -infinity to 1, not including 1. Then union what? All the numbers to the right of 1, not including 1. There. That's the domain of that function.